B. I was looking a little bit at the website DNR has on this before the talk. It's a great website, a lot of resources on there, and if you get a chance, when you get a chance, check it out. There's a lot of good information on there to check out and help us with the various projects that we're involved with. Vanessa got her beginning at the DNR. Told me she's been working there for 4 years. Is that 5 years? And started working in surface water monitoring out in Marshall, doing yeoman's work, taking water samples for a long time, and now she's doing the County Geologic Atlas work. She writes supporting the development of new procedure documents, planning and conducting field work, training team members, managing data, and writing individual county atlases. So with that, I'll give it over to Vanessa.
Good morning, everyone. So like you mentioned, I'm Vanessa, and I'm going to talk about the County Geologic Atlas program as a whole, and really I'm going to focus on the Part B, which is what we do at the DNR. I always like to start kind of our overview presentation with a kind of question for everyone here. Who all knows what a County Geologic Atlas is? All right, good numbers, and do you use them on a regular basis at all? Anyone? Couple? Okay. So to kind of start out, the County Geologic Atlas program, it started in the 80s at the Minnesota Geologic Survey. In the beginning, the Geologic Survey was making maps of what the geology was across the county, and if there was any initial hydrologic investigations, they were done at the Minnesota Geologic Survey. And then in about the early 90s, or right at 1990, the DNR came in and we started doing, we split the atlas into 2 parts. The Part A is done by the Minnesota Geologic Survey. They map out all of the geology. Typically, you'll find a place of information about the bedrock units, the quaternary units, the superficial units, as well as depth to bedrock and sand models in the Part A. And then at the DNR, we do the Part B. We follow after the Part A, and what we're doing is we're imposing hydrologic properties onto those geologic layers that were mapped by the Geologic Survey. So these are just status maps of where each of the, where we're at in each, the MGS and the DNR across the state for mapping the state. The end goal would be having maps across the state. So the map on the left here, this is the progress the Geologic Survey has. Anything in red already has a completed Part A. Anything in green, they're currently working on. And there are some atlases that are in purple. Those are actually atlases that they made them back in the 80s, early 90s, and there's enough interest in those counties that they're now going back with new updated information and updating those atlases. And then on the right, this is the progress at the DNR for the Part Bs. We kind of follow the Part A. If there's not a Part A completed, we can't start our Part B and impose our hydrogeology on the geologic layers and maps. So on the right here, anything that's kind of the medium shade of blue, those are things that both a Part A and a Part B are done. The light blues are ones that a Part A is completed and a Part B is started or in progress somewhere. And then dark blues are those ones that are under revision or being updated. To note, the only thing missing, this is up to date, the Part B, except for Wadena and Becker, we've started prepping those for work that we're starting this summer. So kind of, we like to think of it as a pyramid, the atlas as a whole. So the foundation is done by the MGS. You know, you're locating all of the wells across the county. You're going out, you're doing test drilling, entering new data as you get it about the geology. And then from that, you're developing surface and subsurface geologic maps. You're mapping out where things are on the surface and the layers into the subsurface. And then the top portion of the pyramid is what we do at the DNR, the Part B. We're looking at what the hydrogeology is in those geologic layers, and in order to kind of confirm some of the maps that we end up making, we actually do water sampling and collection and lab analysis to kind of get an idea of what the water chemistry is like, looking at the water. So I'm going to kind of step you through like the process of starting a Part B. So The part A is done. We have all the mapped geology, and our first step always, the part B is looking over and really getting a good idea of the part A. So we'll get a county, we'll get a really good basis for what the geology is across the county, and we'll look through everything that the MGS has provided, both their digital files as well as the reports that they put out, to see how everything is working and getting a good conceptual framework for where water might be flowing and where people are using water resources. We'll also try to do a little bit of due diligence to try to see if there's any other groundwater reports or studies or geologic reports in the area, so just a little background. After we're done with that, we start compiling a file of wells. We're looking at a point file in GIS. We compile a well file by starting out with all of the verified CWI locations across the county. And then with that file, we also look a little more detail into wells that the DNR manages. So we'll look at observation wells and MPARS, which is our permitting wells file, and we'll integrate that data in and do a little more due diligence on location verifications on those wells specifically to get the best possible locations based on our judgment. Then, once we have all of these wells compiled into a point file, we use our GIS tools to look in the subsurface. As part of the Part A, they provide cross-sections along. So this is an example in Morrison County here, what the well file would look like. They have 1 kilometer spaced cross-sections across the entire county, and they develop cross-sections along each one. So a snapshot of what's in the subsurface based on their geologic mapping at each of those 1 kilometer spacings. And so to show an example, this is cross-section 17 up here. This is the subsurface cross-section of it. What we do once we have our well file is we protect all of our wells. The casings are the white and the little red dots are all of the streams. And we go through and we assign an aquifer code based on the geologic unit to each of the wells if we can. So we're trying to get an idea of what water resources are really being used, and it'll give us an idea, baseline understanding of where should we be focusing, sampling, what are people really using. So once we've done that, we've gone through, we've assigned aquifer codes, we go out and we look to see if there's any other existing chemistry data already collected for water data. A lot of times we get this from the Department of Health. They have a lot of municipal wells information, and we can get an idea of, sometimes they'll have tritium data, which gives us an idea of how long it's taken from water at the surface to get to these different aquifer units. We'll look at chloride data and nitrate data to try to identify sensitive aquifers in advance, and it gives us an idea of where we might want to focus our sampling. And then we kind of do a cross-section by cross-section, depending on how many wells are in the county. We try to focus our sampling along cross-section so we can get an idea across a cross-section and with depth, what type of chemistry we're seeing, where we're seeing sensitivity. In this instance, you'll see these darker colored cross-section lines. Those are the ones where we focus our study. And then as far as going out and doing actual water chemistry sampling, what we do is in each county, we'll send out about 1,000 postcards to homeowners. So we'll use parcel data, and in this case, you'll see all the gray dots. Those are all wells that we sent postcards to homeowners requesting permission. And then based on that response, we take a subset of about 90 to 100 wells, depending on the county, to go out and actually sample and look at chemistry across the county and with depth. So then we go out and we collect the water samples. These are exciting. We go out, we do takedowns when possible, but we take into account the fact that these are domestic wells largely, and we don't want to knock too much stuff about in their well. And then we do stabilization. We run water for about a half hour or so. We clear out the casing, as well as monitor on-site chemistry and collect water samples. And then once we collect the samples, we send them to the Department of Ag lab now. We do cations, anions, trace metals. We also collect tritium, stable isotopes. And then after we do our initial data run, we do a subset of about 10 C14 samples to get the ages on later, older water. So now we've gone out, we've collected the samples. Usually there's about a time lapse of a few months there where we're waiting for data to come back. In that time is when we start actually drafting some of our maps that we're planning to include within an atlas. So I'm kind of going to shift gears into the GIS and kind of what we do and what maps we make now. So the first, I'm going to talk about kind of the flow system that we make maps of groundwater flow, and then I'll move into water chemistry.
I was looking a little bit at the website DNR has on this before the talk. It's a great website, a lot of resources on there, and if you get a chance, when you get a chance, check it out. There's a lot of good information on there to check out and help us with the various projects that we're involved with. Vanessa got her beginning at the DNR, told me she's been working there for 4 years. Is that 5 years? And started working in surface water monitoring out in Marshall, doing yeoman's work, taking water samples for a long time, and now she's doing the County Geologic Atlas work. She writes supporting the development of new procedure documents, planning and conducting field work, training team members, managing data, and writing individual county atlases. So with that, I'll give it over to Vanessa.
Good morning, everyone. So like you mentioned, I'm Vanessa, and I'm going to talk about the County Geologic Atlas program as a whole, and really I'm going to focus on the Part B, which is what we do at the DNR. I always like to start kind of our overview presentation with a kind of question for everyone here. Who all knows what a County Geologic Atlas is? All right, good numbers, and do you use them on a regular basis at all? Anyone? Couple? Okay. So to kind of start out, the County Geologic Atlas program, it started in the 80s at the Minnesota Geologic Survey. In the beginning, the Geologic Survey was making maps of what the geology was across the county, and if there was any initial hydrologic investigations that were done at the Minnesota Geologic Survey. And then in about the early 90s, or right at 1990, the DNR came in and we split the atlas into two parts. The Part A is done by the Minnesota Geologic Survey. They map out all of the geology. Typically, you'll find a plate of information about the bedrock units, the quaternary units, the superficial units, as well as depth to bedrock and sand models in the Part A. And then at the DNR, we do the Part B. We follow after the Part A, and what we're doing is we're imposing hydrologic properties onto those geologic layers that were mapped by the Geologic Survey. So these are just status maps of where each of the, where we're at in each, the MGS and the DNR across the state. For mapping the state, the end goal would be having maps across the state. So the map on the left here, this is the progress Geologic Survey has. Anything in red already has a completed Part A. Anything in green, they're currently working on. And there are some atlases that are in purple. Those are actually atlases that they made them back in the 80s, early 90s, and there's enough interest in those counties that they're now going back with new updated information and updating those atlases. And then on the right, this is the progress at the DNR for the Part Bs. We kind of follow the Part A. If there's not a Part A completed, we can't start our Part B and impose our hydrogeology on the geologic layers and maps. So on the right here, anything that's kind of the medium shade of blue, those are things that both a Part A and a Part B are done. The light blues are ones that a Part A is completed and a Part B is started or in progress somewhere. And then dark blues are those ones that are under revision or being updated. To note, the only things missing, this is up to date, the Part B, except for Wadena and Becker, we've started prepping those for work that we're starting this summer. So kind of, we like to think of it as a pyramid, the atlas as a whole. So the foundation is done by the MPS. You know, you're locating all of the wells across the county. You're going out, you're doing test drilling, entering new data as you get it about the geology, and then from that, you're developing surface and subsurface geologic maps. You're mapping out where things are on the surface and the layers into the subsurface. And then the top portion of the pyramid is what we do at the DNR, the Part B. We're looking at what the hydrogeology is in those geologic layers, and in order to kind of confirm some of the maps that we end up making, we actually do water sampling and collection and lab analysis to kind of get an idea of what the water chemistry is like, looking at the water. So I'm going to kind of step you through like the process of starting at Part B. So the Part A is done. We have all the maps geology, and our first step always at the Part B is looking over and really getting a good idea of the Part A. So we'll get accounting, we'll get a really good basis for what the geology is across the county, and we'll look through everything that the MGS has provided, both their digital files as well as the reports that they put out, to see how everything is working and getting a good conceptual framework for where water might be flowing and where people are using water resources. We'll also try to do a little bit of due diligence to try to see if there's any other groundwater reports or studies or geologic reports in the area, so just a little background. After we're done with that, we start compiling a file of wells. We're looking at a point file in GIS. We compile a wells all file by starting out with all of the verified CWI locations across the county. And then with that file, we also look a little more detail into wells that the DNR manages. So we'll look at observation wells and MPARS, which is our permitting wells file, and we'll integrate that data in and do a little more due diligence on location verifications on those wells specifically to get the best possible locations based on our judgment. Then, once we have all of these wells compiled into a point file, we use our GIS tools to look in the subsurface. As part of the Part A, they provide cross-sections along. So this is an example in Morrison County here, what the wells all file would look like. They have 1 kilometer spaced cross-sections across the entire county, and they develop cross-sections along each one. So a snapshot of what's in the subsurface based on their geologic mapping at each of those 1 kilometer spacings. And so to show an example, this is cross-section 17 up here. This is the subsurface cross-section of it. What we do once we have our well file is we protect all of our wells. The casings are the white and the little red dots are all of the streams. And we go through and we assign an aquifer code based on the geologic unit to each of the wells if we can. So we're trying to get an idea of what water resources are really being used, and it'll give us an idea, baseline understanding of where should we be focusing, sampling, what are people really using. So once we've done that, we've gone through, we've assigned aquifer codes, we go out and we look to see if there's any other existing chemistry data already collected for water data. A lot of times we get this from the Department of Health. They have a lot of municipal wells information, and we can get an idea of, sometimes they'll have tritium data, which gives us an idea of how long it's taken from water at the surface to get to these different aquifer units. We'll look at chloride data and nitrate data to try to identify sensitive aquifers in advance, and it gives us an idea of where we might want to focus our sampling. And then we kind of do a cross-section by cross-section, depending on how many wells are in the county. We try to focus our sampling along cross-section so we can get an idea across a cross-section and with depth, what type of chemistry we're seeing, where we're seeing sensitivity. In this instance, you'll see these darker colored cross-section lines. Those are the ones where we focus our study. And then as far as going out and doing actual water chemistry sampling, what we do is in each county, we'll send out about 1,000 postcards to homeowners. So we'll use parcel data, and in this case, you'll see all the gray dots. Those are all wells that we sent postcards to homeowners requesting permission. And then based on that response, we take a subset of about 90 to 100 wells, depending on the county, to go out and actually sample and look at chemistry across the county and with depth. So then we go out and we collect the water samples. These are exciting. We go out, we do takedowns when possible, but we take into account the fact that these are domestic wells largely, and we don't want to knock too much stuff about in their well. And then we do stabilization. We run water for about half hour or so. We clear out the casing, as well as monitor on-site chemistry and collect water samples. And then once we collect the samples, we send them to the Department of Ag lab now. And we do cations, anions, trace metals. We also collect tritium, stable isotopes. And then after we do our initial data run, we do a subset of about 10 C14 samples to get the ages on later, older waters. So now we've gone out, we've collected the samples. Usually there's about a time lapse of a few months there where we're waiting for data to come back. In that time is when we start actually drafting some of our maps that we're planning to include within an atlas. So I'm kind of going to shift gears into the GIS and kind of what we do and what maps we make now. So first, I'm going to talk about kind of the flow system that we make maps of groundwater flow, and then I'll move into water chemistry as well as pollution sensitivity maps that we make. So we provide a water table elevation and depth water table map with each of our atlases. The data that goes into each of the maps is we take point data from the NRCS soil survey. We're looking for saturated depths, and we try to remove out with queries perch conditions, so we're just getting the saturated condition depth. Then we also take elevations of surface water features in Minnesota, and then we do static water level elevations from TBAA wells, and those measured during sampling that have TBAA designations. We take all of that point data as elevations, and then we use topo to raster analysis in our GIS to generate a surface. And then I do want to point out that at the DNR, in our group, we now have what are called the hydrologic assessments, and they're statewide versions of these maps. So we have a statewide version of a water table elevation map, and from the water table elevation, we get depth to water table by subtracting that map from the land surface elevation. There is a slight difference in a water table map you will see in our individual county atlas and that in the statewide layer. The statewide layer is compiled at a 60-meter grid. We do a 30-meter finer grid on a county-by-county basis. It's processing and much easier at a 60-meter grid. So just to give you an example of what this might look like, this is Nicollet and Sibley counties. What you'll see is the kind of pinkish color in the northeast or northwest is the high elevations, and then the blue cooler colors are the low elevations. So we're able to identify, water moving south and east, and it's not very surprising to us because this border all along Nicollet and the eastern side of Sibley is the Minnesota River, which is a major regional discharge point. You can also see it's closely following our watershed boundaries that we have from the DNR. And so to continue, there's also a little bit, you can see even some of the smaller creeks, you got some water table contribution. And then this is a very exciting depth to water table map. Nicollet and Sibley County is primarily Des Moines low, kind of clay-rich hills, so it's not surprising that we have a rather shallow water table in these areas. The only area we see deeper conditions is along the Minnesota River, where we have bluffs. Also, our method relies on data, and when you get to bluff regions, it's hard to have data all along that bluff, so it's hard to kind of classify. So it's a limitation a little bit of our method of modeling. That gives us an idea of what the flow system is in the unconfined, shallow settings. We also want to know an idea of what the flow system is like in our buried units. In order to do this, we generate tensiometric surfaces. So earlier I mentioned we make that well file, and then we define aquifer codes for each of the wells. We query down that well file to each of the aquifers and use that point elevation data as well as regional discharge, water discharge locations. So if you, if I go back to Nicollet County here, the Minnesota River is a major discharge point. And so what we've done is we've added points along the Minnesota River valley to kind of tighten the flow to the river a little bit. And so I'll show you on the next slide, or a couple slides, where we added those. And then we, again, just use towboat raster interpolation and clip all of the surfaces down to where the sand bodies of a certain unit exist. So for an example, again, I'm going to stick with Nicollet and Sibley County. We're going to look at unit SG1. It's kind of the middle of the strat column here. In each of the atlases, we do have a stratigraphic column comparing the Part A unit designations to the Part B. In the Part A, they always color it based on source, typically, origin, and of the different types of material. In the Part B, we symbolize it based on sands and gravels, our patterns on our cross sections, and then the gray colors are relative hydraulic conductivities, where lighter grays are more transmissive, higher hydraulic conductivity, and darker grays are more blocky. So this is the potentiometric surface that gets generated by running that across the two counties. Again, just like the superficial water table map, water is flowing from the north, west, south, and east towards the river. And then when we make these maps, sometimes we can identify interesting or abnormal features. Right here near Portland is one big high point that sometimes it would raise questions. You see this, you expect everything to just be flowing to the river. So we can we'll look at this portion of this cross section to try to take a look in the subsurface. And what we see is there's actually this huge bedrock knob there, and that's Precambrian quartzite. It's really impermeable. So our theory for what's happening is water is moving into the subsurface, but it's kind of ponding up on top of this bedrock knob as it moves out laterally. We also, on our cross sections in the Part B, because we do provide cross sections with the Part B, we add in flow lines at the potential lines, and we see that same water flowing out from that bedrock knob with our epipotential lines in the cross section as well. We also, where it's present, we like to generate flow and look at flow within the bedrock units too, and so we can develop some bedrock hydrostratigraphy. We'll just look at a quick example, kind of in the middle here, the lower tunnel city unit. And we just, the same way we generated the first one, we take the points that exist within that aquifer and use towboat raster to generate a surface across the county. And even in the bedrock, we're seeing the same trend of water flowing to the Minnesota in this case. So those are kind of what we do to look at flow within the Part B atlas. Now I'm going to talk about, we make two different types of pollution sensitivity maps, so we'll kind of talk through those. So the first type of pollution sensitivity map that we make is pollution sensitivity of the near surface materials. This map is essentially, we're trying to model how long it takes water at the surface to reach a depth of 10 feet. We use a breakout of, we model the first 3 feet as being soil unit, and the next 7 feet as being a superficial geologic unit. And the way that we get a kind of travel time from this is we take 36 inches and we divide it by a transmission rate, which is based on the type of soil or the type of superficial geologic material. And I'll show you a table on the next slide of what that kind of breaks out as transmission rate. So we take inches, 36 inches divided by an inches per hour transmission rate to get an actual hour value. So we get 3 feet of soil, and we add it to 84 divided by the transmission rate for the superficial geology at a location, and that gives us a travel time to reach that depth of 10 feet. So the transmission rates we use are kind of, for the soil, we base it off of the hydrologic soil group, which is classified by the NRCS. So type A soils are kind of very, very sandy, gravelly, very coarse materials, all the way down to B, which is a much more fine-grained, silky clay material. And we have calculated out unsaturated transition rates for each of those. If you want to know a little bit more about how we reach those numbers, there's actually a procedure document online that goes into a little more detail on that. And then for the superficial geologic texture, we had discussions with the Geologic survey to kind of compare these hydrologic soil groups to soil triangle classifications that are provided by the Minnesota Geologic Survey as part of their official geology map. And then we can assign a unsaturated transmission rate based on that. So an example would be if you had a very coarse situation where you had a group A soil for 3 feet, you know, your unsaturated transmission rate would be 1. So you'd have 36 inches divided by 1 gives you 36 hours. And then say you had gravel and sandy gravel below that, you'd have 84 divided by 1 is 84 plus your 36 would be a travel time. So the way we have a classification for kind of how high a sensitivity is versus very low. We say if something takes hours to weeks, there is less than or equal to 170 hours, that's high sensitivity, all the way down to if it takes months to a year, we say that's very low sensitivity. And then we also have the classification called ultra low that takes more than a year, greater than 8,000 hours. And this is pretty much reserved for the area of the state that's covered by Lake Agassiz Hills in the far northwest part of the state. And then we have a few overlay special condition regions that we don't calculate or show sensitivities for. And they are regions prone to karst. We've done a lot of research and discussions with the MGS about areas with karst within 50 feet of the surface. It's very high sensitivity. So we have a map that's been published between the DNR and the MGS of areas prone to karst that's just really high sensitivity. We have bedrock at or near the surface. In those areas, we don't calculate the travel time because bedrock's right at the surface. And then in the north central part of the state, there's the peatlands that are very, very dense and very, very high water table conditions. We also have an overlay to indicate those areas as well. So in the end, we have a statewide layer for this. This is the whole state, what it looks like. Just as a note, you'll see some kind of abrupt boundaries. What it is if we go back to here, so on the right, the superficial geology data that we use, when we generate this map for a specific atlas, we can use the County Geologic Atlas version of the map, but in some parts of the state where we don't have atlases yet, we use best available data, which can be at much coarser, like 1 to 500,000 scale versus our fine 1 to 100,000 scale atlases. And we are doing occasional updates as we get new atlases to areas where we were using other maps. So this map itself, available as a statewide layer, will be changing through time to reflect new data. And so I just want to give kind of comparative example. So back to our Nicollet and Sibley example from before. If we compare, say, Nicollet and Sibley here, this is a generalized official geology map. It's very fine, calcareous till across all of Nicollet and Sibley counties. And I'm going to compare it to Anoka County up here, which is covered by the Anoka Sandy Plain and very sandy. These huge geologic differences, we hope we see huge differences in our sensitivity maps. So here's Nicollet and Sibley County, low sensitivity across the entire county, which is kind of expected with that dense till at the surface in comparison to Anoka County, where we have those really sandy conditions at the surface. We're seeing those areas of really high sensitivity. So that's looking to a depth of 10 feet. We like to try to also get an idea of what the units at depth, also what the pollution sensitivity is. How we do this is a mouthful acronym called the Cumulative Fine Grain Sediment Thickness Method, the CFGS method. Really, all it is we add up all the fine grain material overlying a certain aquifer. And then we rate it based on how much fine grain material overlies an aquifer. It only looks vertically, and so how it works, this is an example, stylized cross-section. So say you wanted to know, wanted to look at buried sand 1 on the left here, There's only 5 feet of fine-grained material over it. We have our kind of rubric here for how we rate our sensitivity. If it's less than or equal to 10 feet, we say it's very high sensitivity, down to very low being greater than 40. So a cumulative example would be saying 2 directly beneath it. You have 5 feet from the first fill, 7 feet from the second, you get 12 feet total. That moves you into a high designation instead. And on the other spectrum, you can go all the way to the right. You have a situation for very sand 1 where there's 41 feet of till overlying it. That gives you a very low sensitivity rate. And we do this across an entire county because as part of the Part A, the geology portion, they actually generate till thickness factors. So every till unit that they generate, they have an accompanying thickness factor. So we can just add together all tills that overlie a specific sand cumulatively all through the strat column to give us a total amount across the entire county. And so once we generate this map, I'm just going to do a little, we then check it and do a little bit of verification using that chemistry data that we collected. Our biggest thing that we compare it with is tritium data. Tritium is a isotope, a radioactive isotope of hydrogen. It was elevated in the atmosphere when they were doing nuclear bomb testing back in the 50s and 60s. So if there's any presence of tritium in the water that we sample, it's saying sometime in the last 50 or 60 years, some type of water is getting to your water resource, where you're pulling your water from. At the DNR, we have kind of 3 groups that we do. Vintage is anything that's less than 1 tritium unit, and so that water that hasn't gotten any recharge in the last 50 to 60 years. And then mixed and recent values have some amount of tritium in it. So an example in Nicholas-Sibley County, so this is Aquifer Unit SHSD. It's the first buried aquifer. You can kind of see, there's quite a few areas of like moderate to high sensitivity, but other areas are full, sections of low sensitivity, like the central part there, central region. And then our kind of visual inspection check with the tritium data is there's a point right in the center southern part of Sibley County there that blue X is color-coded based on the tritium value. Blue is vintage, we're seeing old tritium in that very low sensitivity area. And then, whereas in Nicollet County near Cortland, there's actually a mixed value that appears to be in the very low section, but you can see that it's very close to all of the higher sensitivity areas, as well as this is also that area we talked about on the potentiometer surfaces that has water flowing outwards from it. So water is actually flowing from those higher sensitivity areas to the lower sensitivity area, giving us that mixed value. The black value on there as well, that's the chloride content. So 17.6, higher than 5, usually designated with a chloride to bromide ratio. That tells us that it's probably an anthropogenic source. So we're seeing recent water in the subsurface. And then we do this systematically all the way through our stratigraphic column, all the way down to the bedrock surface. So this is the bedrock surface sensitivity. In Nicholas-Sibley County, we just have high sensitivity where we have down cutting in the Minnesota River Valley. But I should also point out, we also have a statewide, not quite statewide, atlas-wide layer that we're continually updating that has all of the different pollution sensitivity maps of the bedrock surface kind of mosaic together, so that is available as a layer that you can get a hold of. So now I'm going to talk a little bit about water chemistry information. Some of the stuff we kind of look at in a little more detail in our atlases. So we look at groundwater recharge sources. We look at stable isotopes of oxygen and hydrogen. So oxygen and hydrogen both have different amounts of isotopes. So they have a light isotope and a heavy isotope. If water sits at the surface in a lake or a wetland for an extended period of time, preferentially, those light isotopes will evaporate out and you'll get a heavier signature in water. So we can kind of parse out water that sat at the surface that then recharged the subsurface system. And then in a special case that I'll talk about, you can also have very, very light isotopic water if it was recharged in, say, ice age conditions or as snow. And then we also have groundwater residence time indicators. So this is the tritium that I discussed before. We can get an idea if water in the last 50, 60 years has gotten into a water resource. Or we also have carbon-14 data. That's to age or get the age of water older than 100 years, and you can get an age date between 100 and roughly 35,000 years. And we have a pretty good data set on that. And then we also do a little bit of looking at just inorganic chemistry in water in general. So to talk about the stable isotopes that I mentioned, when we are looking at stable isotope data, you usually just plot on a standard regression that isotope, or the delta O18 value, so your oxygen percentage or amount, and your hydrogen against each other. Anything that falls as precipitation, you'd expect to fall along this black line. That's the meteoric water line. It's pretty applicable across. You can make local lines, but they don't change too significantly. So we actually use a meteoric one that's across the entire world. And so anything that's plotting along that, you'd expect it fell as precipitation and went right into the subsurface. But you can also see kind of a trend that's much lower than that line off to the right and upper corner. Anything that plots along that line, that's giving, it's called, you can put a line on that, it's called the evaporation line. Those are where we're seeing evaporation in the samples. Kind of confirmed by the light blue color there. Those are all lake samples. So that's kind of, you can look at the trend in lakes. And anywhere you see samples that are red, kind of in that line past cloud, those are indications of wells that at some point have been recharged by water that sat at the surface for a while. Another interesting thing to note on this graph is you can look at this very light data down here. So you get lower on the oxygen and hydrogen as you go to the left and down. And these values here are very, very light isotopically, and if you look at where they're located in the state, they're actually located up near Clay County, underneath that Lake Agassiz clay that has very, very low transmission rates. This is letting you know that not a lot of water is getting down since the last ice age to these depths. This is just showing you, we've been collecting C14 samples for about the last 25 to 30 years. We work closely with the University of Minnesota, with Kelvin Alexander and Scott Alexander. And so we've compiled this amount of data, and I should note, this is not actually the most up-to-date data set. We have an additional 4 or 5 counties that haven't been included in this. They are just currently revising the model, and a new report and set of data should be released in the next 2-3 months, hopefully. So these are data that is widely available. If you're interested in looking at any of it, we can definitely get it to you. We then look at the Kuiper plot of general chemistry. So we're plotting cations versus anions to maybe see if there's any indication of how water is evolving in a county through time. The key thing to note is the points on here are color-coded with that tritium value. So the green and pink are things that have recharged in the last 50 to 60 years, whereas the blue samples are not showing any. And if you look at the cation triangle on the lower left, you can see all of your younger stuff is kind of up to the left, high amounts of calcium, whereas your older samples seem to be closer, moving downwards to the right. That means that through time you're getting cation exchange. What's happening is your calcium is being replaced with sodium through time. We can also, now that we have, this is actually what our data set looks like now. I just pulled these this week. We can try to identify more of a statewide trend. Now that we're getting such a comprehensive data set, we can try to identify interesting chemical trends, not just on a county-by-county scale, but try to look outside of it. One area that we've kind of looked at is, so if you look at these highlighted samples, these are all, if you look at our Kaiser plot, things that are high in sulfate. And so we're seeing kind of an interesting divide of, this is kind of where the Des Moines lobe has extended through time, and you have high sulfate values underneath the Des Moines lobe hill. And to zoom in to see a kind of really unique specific case, Nicollet and Sibley County is right here, and it's right on the border of where that divide is happening. And you can actually plot the two counties together and look at percentages. You know, our orange and red are our higher sulfate values, and greens are lower. And it actually seems to follow a pretty straight along this Hydrogeology boundary, which we don't have empirical proof of this, but it is very interesting to see this trend and identify it with the data. So we'll also include in the atlases some information about groundwater use. At the DNR, you're supposed to, in the state, have a permit or a groundwater permit if you pump more than 50,000 gallons per day or 1 million a year. And so we have that data readily available to us. This map is showing how much water is being pumped and for what use in Anoka County. As you might expect, largely it's being used for water supply in Anoka County, but there are also other areas where you see a lot of green spots. There is a little bit of non-crop irrigation happening throughout the county. And then we can also look at what types of resources are being used and being pumped to get an idea of how much water is being pumped from the different aquifer resources. In this case, it's a pretty decent distribution between bedrock sources and with just a few buried sand and gravel aquifers as well. And on this map, I just want to point out 2 areas that we're going to talk about on the next slide. So in the northwest part of the county, there's that box that's the Pickerel Lake well nest area. You'll just notice that there's not a lot of water supply happening, no permits, not a lot of permits in this area. We're going to look at a little hydrograph area in that area, hydrograph data in that area, and we're going to compare it to some wells down here in the southeastern part of the county where we see a lot of water supply usage happening. So this is that first area where there's not a lot of water usage. The top graph is showing us precipitation, and the bottom graph is just showing us water levels in a water table, Wanawak and Mount Simon well. And for the most part, you can see it mirrors the precipitation pretty well, and it has just a basic, high in the summer and fluctuates down just seasonally. So we're seeing seasonal variation in this data and not a lot of spikes or any impacts on the data, versus in the Lino Lakes area where we have a lot of those wells, a lot of those MPARS permit wells and high usage. We're comparing actually in this graph water use to our water levels. And as you can see, when we have, say, July 2012, we have a high spike in how much water is being used. We are seeing a direct impact in our water levels, and we can pick that out. In this case, luckily, even though we're seeing those spikes and impacts, it does appear that the water is stabilizing back to the normal level. We also provide, when available, data on specific capacity and specificity within our reports. This is usually just a summary table. The specific capacity values, we calculate them by using CWI data, and we put a few restrictions on what the diameter of the well can be and where the pump is placed, just to try to query out some of maybe the anomalies. I don't know if you guys work with CWI, sometimes there can be a little bit of data entry issues, so we're just trying to parse out solid data in that sense. And then the transmissivity values, we actually, at the DNR, they're currently working on a aquifer properties database. They're working with the MDH and trying to get an actual compilation data set of aquifer tests across the state. And so we work with a group that's compiling that data to get an idea of transmissivities of different units. So just kind of uses, resource protection management, county water plans, just basic planning for a location and drilling wells sometimes are getting used. We've heard many different uses. We'd love to hear more if you have any additional stuff. And then I just wanted to say there are a couple, I've been talking about a county, for the most part, county by county basis scale map. We also have 6 regional assessments that were done in the 90s and early 2000s. Those were done in areas that maybe we weren't quite sure if atlases would be done county by county in those areas. So these are available. They are a little more broad and they don't always have as much detail as the county by county scale, but we like to point out that those are available. And then, as I've mentioned, we also have the Hydrogeology Atlases. Those are the statewide layers for the water table, depth to water table, near surface pollution sensitivity, and then the bedrock surface sensitivity as well. All of these are available by going to our website. I should also plug in that we have GIS files for the majority of the data. You can download the GIS files and use them. So if you go to our website, you can go mndnr.gov/groundwater mapping to reach our homepage. And then to get to this, you just click on Maps and Studies on the left-hand side of the page. The County Geologic Atlases, the first one, that'll get you to the county-by-county breakout, to that status map that I showed you on the first page. We also have a Part A status map on there as well. And then we have the Minnesota Hydrogeology Atlas page that'll get you to those statewide layers that you can download and both the reports and the data. And then we also have the regional hydrologic assessments on there as well. Also, if you go into the resources tab on this page, that's where you can find, if you want to know a little bit more about our exact procedures, we're publishing procedures that we use for the different maps now on the website. And I just want to put in one plug, if you weren't aware of it, we do have the water monitoring and surveys unit at the DNR, and they have data that is available for download and public source for climatology, stream flow for 260 or so sites, 270 sites across the state, lake levels, and groundwater levels across the state, which they've instrumented a lot of stuff with continuous monitoring. So in a lot of instances, we can get continuous monitoring. So kind of in conclusion, the County Geologic Atlas Part B includes information on groundwater flow, chemistry, and pollution sensitivity. The reports, data, and procedures are all published online and publicly available. And Atlas reports cover much of Minnesota, and through time we're getting more and more capabilities to look at things more on a statewide basis and not just a county-by-county basis. So I just have my last slide here is if you're looking for a specific type of data, here are a bunch of website sources for each of the different types of data I mentioned. So, questions?
I have a question.
Yeah.
Back to your data on looking at Lino Lake in that area.
Yeah.
So would it be fair to say then there's that indicating over usage in water consumption, or is that?
In this case, I mentioned that water levels, yes, you see a spike down when there's high usage, but you also see rapid recovery back to about the same baseline level. So I wouldn't say it's over usage. Jim, it's your atlas. Any?
It's a limited data set, so that's sort of the first caution. It's only a few years. But for this data set, it looks like it's recovered.
So then how would that come into play if, say, there's consideration for an additional municipal high-capacity well going into the future? How would that affect the permitting for that? Or?
We have a group that looks at the permitting issues. We don't do that. And they would be looking at these sorts of things and taking that into account in their decision making. From working with them over the years, I'm guessing they wouldn't see any red flags.
Yeah.
Mostly the places that we run into trouble, because we have a pretty robust precipitation and relatively robust aquifers that we're using, is in specific cases of groundwater surface water interaction where there's particular streams, rivers, lakes that are connected and close by. So that's what they'll do when they look at that, is they're looking for those kind of what's close, what's connected, and what's the pumping value. Sort of long-term issues, I mean, we do have some guidelines for how to understand sustainability of use, but again, the aquifers are pretty robust, and so you can hit them pretty hard, but at some point, yeah, you start seeing a trend down over the decades, and that happened with the Mount Simon, and why we changed the laws 20 years ago, because the Mount Simon was in a long-term free fall, and because of overuse, and it's rebounded, you know, since we stopped using it for everything and misusing it. So the close connection is really with rivers and streams and stuff.
And domestic well users.
Interference.
There could be a domestic well user that's nearby that's hypothetical as well that could be affected during the testing period of that well, and this would sort of play into it, but that would override this sort of kind of.
Yeah, if you had a shallow house well right next to that QBAA, you know,
There might be an issue.
it might be an issue if yours was a shallow well. So.
I've got a question. I'm curious